Alright, hell yeah. We got material mechanics, and I'm going to work some magic here because this problem was kind of complex for me. And so what I'm just going to do is going to go through what I think the answer is. Hopefully we do it right. We're going to say we have to use energy. This thing is going to be loaded up to there, going to be dropped. Under free fall, it's going to land right here in shock load. So we have an impact force on this cord. Has a E of 2.1 gigapascals, so it's not 400, so it actually is. It's a nylon cord. See how I just looked at this and it's a low number because I think 200 gigapascals is steel. So this is just 2. Okay. All right, let's do it. So our equilibrium equation says that the center of mass of this is up there, and we need to know its height. You know what I mean? And actually, we're gonna kind of get a rough estimate because hey, if you know anything about so if this was in the vertical, like the center of mass right there is when it's like at this angle, right? But if we went to vertical, whoa, the center of mass would be just like hardly any different. So what we're gonna say is we're just gonna assume that it's vertical and then falls from here. And the energy equation from here to there, even if you don't believe me, and at the end of this video we're going to prove why this is, but the energy is just mgh. We've all seen that. And so if this is the potential energy initial, well, due to conservation of energy, there's no force that's like throwing it down, so we're not like adding any extra force, so that's 0. So then when we get down to here, upon impact, our velocity is going to be 0 after it impacts and stretches. And we're just going to assume just fully damp, like the thing just comes to a dead stop. That's ideal. It's not going to bounce or anything. But where we're going to say, hey, then that's equal to the energy that gets put into a cord, which is a spring. So the energy in a spring, you might know this one, it's 1/2 kd squared, you know what I mean? And if we were just wanting the velocity before it impacted, well, that'd be 1/2 mv squared, you know what I mean? So at the end of the day, we could say, well, I want to know the velocity. Well, hell yeah, m's cancel, and then bring the 2 upstairs, so you got 2gh, and then the square root of it, baby. And then just, instantly you got the velocity upon impact. Cool. But that's why energy is so magical, because we're going to take that potential energy, mgh, and we're going to equal to it all the energy getting stored into a material. Any material is just a spring, so the force of a spring is k change in length. And the energy of that is force times distance. Well, the distance is change in length. So you got change in length again. Look at this. And then the force is actually the force max divided by 2, because you need the force average times, change in length. And change in length over here is force over k, so you would get it twice. You would throw in force over k here. Now you'd get force max squared divided by 2k. Cool. But anyway, that is equivalent to this, but that's for when we finish. We're trying to get this in 10 minutes. All right. So you got 1/2 kd squared, and now you're going to rearrange for what? What the hell do they even want to know? Oh, well, what's the max? Oh, check this out. What is the max stress in the cord? So we will go back to this, maybe. We'll probably just use the equation for a spring. Says, hey, if we can find the change in length, we can figure out the force. And you might be like, well, we don't know k. Okay, well, let's go back to the basics. First equation for material mechanics is force over area. Always write that one in. This I call strength. And then we got stretch. You know what I mean? This is stress and this is strain, but call this one strength and this one stretch. And then we got change in length over L. And then the equation that links the two is due to material property of how elastic it is, or kind of how stiff it is, but it's going to be EE. There you go. And you probably should write it the other way, because this is the proportional constant. You're basically saying, hey, strength is proportional to strain with a constant, and the constant is E. Booyah. All right, so let's solve this. Why would we solve this for anything? Well, you're going to solve it for the distance that this thing's going to stretch the cable. And if we know it stretches the cable, then we're going to get induce a force. And what the hell is K? Well, you rearrange these, so let's do it. Let's do it. We're going to take this one. This is force over area. This is change in length divided by length, and then we got E. So we're going to rearrange for the force or change in length. Let's rearrange for change in length. L goes upstairs, so you're going to have FL. E goes downstairs, FLEA. So change in length is FLEA. Might as well solve for force too. Just rearrange it. So force is, hey, A goes upstairs, so you're going to have change in length EA. I always maybe put EA like that. It's just you know, that's what they do. It doesn't matter. Anyway, so there you go. So now what the hell are we trying to get at? Well, if we found the distance, we would be able to be like, whoa, that's this distance. That's this distance. And we already know the modulus of elasticity in the area and the length of the cord. So, booyah, we could find that force max. You know what I mean? The force at this distance D. And, you know, so how do you solve for D? Well, you take the 2 upstairs. So you got 2 mgh. Divide by K, and then the square root of it. All right, there you got D. So if you want to do this all in one crazy step, you would throw this right into there. So we're going to get force max. And like I said, we're starting from just vertical. You know what I mean? Who cares what this? Who cares what this difference is? You know, whatever angle. Just I simplified the problem, and we'll get a bigger stress, but it won't be that much bigger. Okay, we just want to quickly get to the answer, and we might. Not in 10 minutes, but we got 3 more minutes. Here we go. So, yeah, we throw this into there. So we're going to have, hey, the square root of 2 mgh divided by K, so that's all the square root, EA divided by L. Cool. And is that literally going to give us the max force? Yes, positively. And so what the hell was H? H was this height, which was L divided by 2. That was that mg. Remember mgh? Well, H is L over 2. So, you know what I mean? And forget this. We're not even going to simplify. But we're going to go 2 mg L over 2. Cool. So the 2's cancel. And then the square root of that, EA divided by L. All right, well, let's plug and chug. So now the mass is 1. Gravity is 9.8. So we're going to have 9.8. Length is 0.5. So we're going to have 0.5. I'm not worried about units because we're just going for it. Oh, what the hell's K? You know what I mean? Yeah, I guess we need K. Yep. So this is kind of tricky, but you go back to force is equal to K change in length. Look at this. Hey, we said force is equal to change in length EAL. So, hey, K is EAL. So maybe we should simplify this a little bit. So you're going to have, oh, we don't need to, but I think we should. We might even get a new sheet of paper. And we're going to run out of time. We're not going to be able to do this but in 10 minutes, but we're pretty close. So we're going to have force max is equal to 2 mg L, and we can get rid of the 2. We've already done that because the H was L over 2. All right, divided by K. K is EAL, so that, oh, you're going to get an L squared. Cool. And then that's gonna and then multiply by EA, all divided by L. Man, I don't like doing problems this way, but we'll probably nail it, hit it out of the park. So what I would do is square root the hell out of everything. You know what I mean? So now you're gonna have m to the 1/2 g to the 1/2 L squared to the 1/2 is just L, and then you're gonna have E to the 1, A to the 1, but now you're going to divide that by E to the 1/2, A to the 1/2. See how it's just going to make our life kind of easier? Where the hell does L go? Is it all divided by? Yep. Oh, yeah, this is still in the square root. All right, one more time on the clock. Alright, so maybe this probably isn't the best way, but see how all these things were in the square root? You know what I mean? And we took them kind of, not out of the square root, we just kind of made them look sensical. And then, yeah, so so the L is just down here. So we're gonna... Yeah, the L just cancels right out. It's not even so the force is not even a function of this length at all, I guess. Hopefully we did that right. Probably not, though. So this L to the 1 cancels with that L to the 1. And so now you're going to get, and these divided by EAs goes to up to, so the E is just 1/2 A to the 1/2. So now we're going to have MGEA square root of it. Is that it? Doesn't that say mega? Holy Toledo. Too close to the political seat. But anyway, and I'd be surprised if this even works. I don't do problems like this because there's no... You just lost everything. You know, the second you just start using symbols, you lose any sort of relationship with, you know, potentially the potential of area increasing, or, you know, anyway, so let's throw it in. We're going to have mass is 1, gravity is 9.8, E is 2.1 times 10 to the 9, and area is, well, we got to be a little careful. Not really. But mass in kilograms times meters per second. So as long as this is in kilograms and this is meters per second squared, guess what that is? This is 1 Newton, baby. And then this is newtons per meter squared. So we need to multiply the area by meters. We don't have it in meters. We have it in millimeters squared. But you should know, maybe you don't, divide by 10 to the 6. Now we got meters squared. So those cancel. And now we're just left with, I don't know what we're left with. We're left with just newtons. Oh, we should have newtons squared. Where the hell's our other newton? Oh, I see it. Because this is newtons per meter squared. The meters cancel, so now we got a newton there, and this is our newton there. And then we're going to square root those 2 newton squares, and guess what? We're going to get 1 newton. You know, as our units, not just 1 newton. Anyway, alright, so we'll do this one first. 2.1 times 10 to the 9. And times 0.98 times 30 divided by 10 to the 6. And no, we did not get the right answer. Well, you never know. Maybe we hella didn't. That was a horrible way to do that. So now I guess we have to slow down. That's why you don't do problems that way. You know what I mean? Yeah, that was an insane way to just get a wrong answer. And that's not even how I start a lot of my problems. So how I start problems is like, hell yeah, let's get the strength equation, force over area, take a little breath. Strain is change in length over length. And then the relationship between them. Strength is stretch times modulus of elasticity. We're still going to do it. We're still going to go back to this MGH is equal to the energy of the potential energy of the height fall, and we're going to say it's vertical from there to there, and that's going to be L divided by 2. So now we're going to have MGL divided by 2, and this is equal to 1/2 KD squared. And but I guess, yeah, well, what the hell is K, and what the hell, and we're kind of solving for D. But you rearrange this, and you can get change in length is equal to FL over EA. If you don't see that, hey, you put both these into there, and then you just solve for change in length. You know, you should always do that, but you should be able to memorize this one. Change in length is FLEA. It kind of spells flea. I have no idea. It's a dumb reference. But anyway, at least you kind of know. And always put the EA in this order. We've already said that. Okay, so once we find change in length, we would be able to find the force. That's what we were getting at. But then we rearrange this. Or we know the force of a spring is K change in length. So we rearrange this and make it look like that. We're going to have force is equal to EA divided by L change in length. So look at that. K is equal to EA divided by L. And there you go. And then once we find the change in length, we would be able to put it back into this equation and find force. How did this not work? Because if we find the change in length, so we'll do that first. Then we would put it back into this equation. Why couldn't we just do that all in one go? Should we try one more time? Or I guess not. I guess not. We're just gonna plug and chug. So we're gonna rearrange this. It's gonna be 2mg L divided by 2. So I already did a couple things. And then divide by k and the square root of it. So that's d, you know what I mean? So we just rearranged everything and solved for d. And this is going to be 1 kilogram, 9.8. Length is 0.5 meters. Oh, we run into the same problem. What the hell is k? Well, it's EA divided by L. So let's just do that totally separately. This is 2.1 times 10 to the 9. Times area, which is 30 divided by 10 to the 6, divided by 0.5. Cool. So we're 2.1 times 10 to the 9 times 30 divided by 10 to the 6 divided by 0.5, stored as alpha k. So this is stored as alpha k, and it's a normal number. 126,000 newtons per every meter that this cord stretches. You know what I mean? So, man, that doesn't seem right either. Oh, that's a bummer. Isn't that the units on this? Yeah, newtons per meter. What am I missing? What am I missing here? Shouldn't this be way bigger? 33 times 10 to the 6. Yeah, I mean, holy Toledo. Is it this area that I'm messing up? Because, oh, holy hell. No, we're still good. This is E. This is E and that's A. But yeah, 2.1 times 10 to the 9. That's a really big number. 30 millimeters squared divided by 30 divided by 10 to the 6. Yeah, times 30 divided by 10 to the 6. Yeah, that's all right. And divided by 0.5. I don't know. Oh, it's a nylon cord, I guess. Oh, for the love of God. No, we were right. We were right at the beginning. My goodness. You know what I mean? Apologies. Because this was 100% right. But this just solved for force max. You know what I mean? And then I just looked at the answer in the back of the book. And the answer is stress. But stress is in like PSI. Or for this problem, it's newtons per meter squared. You know what I mean? And so stress is force divided by area. Well, guess what? We just solved for force. We got to divide this by area. So we can go back and figure out what number that was. I don't think we can. But yeah, well, let's do this. So this is this was 9.8. Yes, we were so there. We just kind of got confused. 2.1 times 10 to the 9 times times 30 divided by 10 to the 6. Okay, cool. And then the square root of that number. Nah, I guess so. Is that right? We'll try it one more time. 2.1 times 10 to the 9. Oh, yeah, because I got that same number. I just didn't square root it. Like, I was expecting a really big number, and I wasn't. I thought I was. Anyway, the answer in the back of the book was 33 megapascals, which is 33 million. But that's newtons per meter, and 1 newton is actually just a quarter pound. It's not very much, and that's spread over a distance of 1 meter. You know, that's 1 newton meter, and that's 2 newspapers. It's the weight of 2. It's hardly any pressure at all. That's why you have to have 33 million of those. That's 66 million newspapers stacked up. That's the weight. All right, more time on the clock. But yeah, the 66 million newspapers is the weight that this cord feels. All right, so this was a kind of a nice simple equation, but it just gives us force max. Then we got to divide it by area. So now we got to divide this by area. So let's do that. Let's do this all in one step. Let's go back to what the hell this was. Now we're gonna do force max divided by area. Well, that's going to be the stress. And this is going to be m to the 1/2, g to the 1/2, e to the 1/2, a to the 1/2. Anytime you're combining variables, this is just a surefire way to not mess up. And now we have a 1. And you can just take it upstairs, -1. So now what we do have is we have the square root, so these turn into a -1/2, or just a to the 1/2 downstairs. You know what I mean? So now we have the square root of mge divided by a, and now this should give us the answer that we want. Mass is just 1, so we got 9.8 times 2.1 times 10 to the 9. Divided by the area, which is 30, I guess we'll do some parentheses here so we don't mess up, times 10 to the -6. That's the same thing as dividing by 10 to the 6. This is in millimeters squared. You got to divide by 10 to the 10 to the 6, or multiply by 10 to the -6 to actually get meters squared. Make sure that your units are good to go. All right, and then we're going to get an answer there, and we're going to square root the hell out of that. And we get the stress in the cord, and we're going to divide by 10 to the 6, and we get 26 megapascals. Now I know it feels like we did something wrong, because we should get a higher number, and I don't know where I'm going wrong. Okay, so now we definitely need to slow down. That's why I don't do problems that way. Because, doing problems with letters is just absolute madness, because you have no idea or way to figure out where your error is. So we do have the spring constant for this cord. It's EA over L. So we do have that stored in our calculator. We're going to run with it. And now we need to... Where's our equations? Do we have one more? Can we do this one more time? Alright, last time. So strength is force over area. Stretch is change in length over length. Strength is equal to stretch and then mod EE, you know what I mean? I don't know. And so we have change in length is force LEA, and then force is change in length EA up top divided by L. The force of a spring is K change in length. Cool. And why can't we? It feels like I want to do this all in one go, but I don't know why I'm making mistakes. So we're going to do it one more time. So we're going to say MGH, which is MGL divided by 2, is equal to 1/2 KD squared. So we can already simplify this and get rid of the 2. So we can say MGL is equal to KD squared. Let's throw in what K is. We already said K was EAL. So we got MGL is equal to EAL D squared. The L pops up there, and we're going to get MGL squared divided by EA. Square root of it, well, hell yeah, that's change in length. You know what I mean? That's D. Okay, and then we would find the force by throwing D into this equation. So we would have force max is K, which is EA divided by L, times this, the change in length, which is the square root of MGL squared over EA. Okay, and then once we get force max, we have to say force divided by area is stress or strength, or PSI, newtons per meter squared is what this problem is. It's a pressure. Anyway, I like to call it strength. So now we have to divide by one more A. Cool. So those A's cancel. So now we have E divided by L, square root of mgl squared EA. And so let's just throw it into our calculator like that. So we got 2.1 times 10 to the 9. We're going to store that as alpha E. We have 0.5. We're going to store that as alpha L. We have the area, which is 30 divided by 10 to the 6. Now that is the area in meters squared. Cool. 9.81 stored as alpha G. Cool. And now let's do it. So we're going to have alpha E divided by alpha L, and then the square root. Oh, we didn't do mass, but mass is just 1, so we're just going to get rid of that. Who cares? And then alpha G, alpha L squared, divided by alpha E, divided by alpha A. And then we did it. Why are we still getting a stress of 26.2 megapascals? For the life of me, I don't understand. Are we not setting up the potential energy right? I guess I haven't solved this problem 100%. I thought I did. But if we set that height, which is half the length, I feel like if we double this, then we would actually get the drop. But maybe not. Maybe not. I don't want to throw in the towel on this one, but yeah, super bummer, man. Oh, hell yeah. Okay, I found my error. I was using this as the length. Well, guess what? I'm confusing length. I always use length as the length of the spring. No. This length should just be who. I don't know. I would call it. I guess we're gonna call it. But this length is the length of the spring. So let's since we caught our error, and I think we can figure this out. So let's go back here. So change in length is FLEA. This length is B. So I'm just going to do B right there. This is B. So now we have force in the spring is change in B. Cool. So now we find D, which is change in B, and then we throw it, and then so yeah. So this MGL, sure. This L, but you know how we combine these L squares? Hell no. Because this is EAB. Oh, for the love of God. And we're not even getting the right answer because we're not even setting up the trigonometry. You know what I mean? Call that phi and call this theta, and then figure out where the hell this height actually is. It's not 0.5. If this length is 0.5, this is not 0.25 meters. It's a little bit less. But anyway, so that's why if we do the easier one, that was just my leg rubbing against the chair. And okay, hell yeah. So where else was this length? Okay, this length is L. That's that length. Anything associated with the spring is a length of B. So where the hell do we even put these together? Yeah, so this is MGLB. So there should be a B right here. There you go. And then so anywhere with this L squared, it's LB. You know what I mean? Which is a factor of 2 because length was 0.5, so yeah, so I was right. You know what I mean? Intuitively, I'm like, hey, this should be 52.4 megapascals, and if you have a drop height that's a little bit lower, you know what I mean? Hell yeah, you essentially. I think it is a square relationship. So it's not just you don't just lower the MGH and half the stress. You know what I mean? You definitely, it's probably a square relationship. Okay, but let's is that it? EA, or what's this L? Oh yeah, this L was this L is a B2. Cool. Let's try that. So we're gonna go alpha E. Oh, we gotta store this as B. All right, more time on the clock. All Alright, hell yeah. So we have B 0.25. Oof. 0.25 stored as alpha B. And calculator's running at it. We got to really do this one. So we're going to go alpha E divided by alpha B, square root. M is just 1, but we need an alpha G, alpha L, alpha B, divided by alpha E, divided by alpha A. Enter. Hell yeah. And like I said, it wasn't just a fact. Well, this length comes up twice. But anyway, so our stress in the cord is 37.1 megapascals, dropped from a vertical height. Now I just don't have the wind in my tonight to actually go through. On another night we'll actually prove MGH. You know what I mean? Why is that energy of this? Why, when you drop it from this height? Well, it's because the force of gravity is only in one direction. So even though this thing's going on a radial path, the only component that's of concern is the drop height from is this distance, but you know what I mean. There actually is no, when this is right here, there's hardly any force, and when there's right here, the force is mg. Anyway, we'll do that for another video. But yeah, the whole point was just to throw numbers at this and get out an answer. But we already messed up because we did everything right except that we got confused on what L was. This being L, usually it's what we're concerned of. This is the material that we're actually changing its length. And that has a force constant of K change in length. K is EA divided by L. Did I get that right? Yes. And then change in length is change in length, force is force, but the L is B, you know what I mean? It's the actual length of the thing that you're stretching out. Okay, so hell yeah, we did it. That was just a quick demonstration of how to use energy. But when I came into this problem, I was not convinced that if you have a hinge on a rod and you drop it, I get that this is the center of mass. I got that. But it just wasn't intuitive to me that this potential is MGH. You know what I mean? It seems like it would have a radial component, but it doesn't. And it seems like, well, I wasn't even worried about that. But it seems, I mean, I guess what I'm getting at is like this. Ah, damn it. All right, one more minute. Bear with me. So this falling, you know what I mean, on a hinge is the same thing as this length just being dropped by a hand from this height, and then dropped, and then the string would catch. You know what I mean? That would be the same thing. The fact that this swings and hinges is very fascinating. The fact that anything, you know, the fact that you would just drop it at that height, that's the same energy. This center of mass is going to have the same velocity upon impact, and we might as well know what the speed of the center of mass is. So let's do that. And it's just the center of mass. Once you know the speed of the center of mass, you know this is 0. Well, you know that's twice the distance. You know what I mean? Because now you have a radial velocity. But anyway, so let's do that. So we're going to do MGH is equal to 1/2 mv squared, and just end the video on that. 2 goes upstairs. We're gonna, and then no masses cancel, so we're going to have 2GH. And don't get confused what the hell H is. It's L divided by 2 is equal to, so that squared is equal to V. H is L divided by 2, so that would be L divided by 2. 2's cancel, and you're going to have GL square root of that. That's your velocity, baby. And you're going to have, and this is just 9.8 times 0.5. That's about 5. Square root of 5 is 2.3. 2.35 meters per second. So let's do that. Square root of alpha G alpha L, 2.2. So anyway, So yeah, it's going 2.2 meters per second, but guess what? Almost instantaneously. And it's not instantaneous. There is a time rate of change that this elasticity will... the energy equation doesn't give you a time. It kind of takes that out of it because you're just integrating over distance. Don't quote me on that, but because you can prove the energy equation, or you can get the same thing of just like, well, what distance is this going to travel when this thing impacts? And you could do it based on time. You integrate based on acceleration. Acceleration is a change in velocity. That change in velocity happens over small increments of time. You throw it into Excel and make very small increments of time, and you're going to have a smaller acceleration, or same acceleration, but that acceleration is multiplied by that tiny change in time. So your change in velocity is slow, is tiny, but that eventually hits zero. You know what I mean? Once it stretches out. So I wanted to do that, but I just don't have it in me tonight. So this video is just like, well, and it's cool to make mistakes. Anyway, enough said on this one. But that's what I wanted to just show. It's just very fascinating that something that rotates around a pivot, center of mass, it don't matter if it's... Because even if, when something rotates around a pivot, it's like almost... it's tipping slowly, and then gravity is affecting it. But all these vectors line up because energy is force vector times distance vector. So this is the path. So the integration of the path is this direction, but the force is in this direction. So when I'm right here, the dot product is 0 because I got force down, distance going that way. And then when I'm here, well, the force is still way down, and the dot product's only a percentage. You know what I mean? So that's what I wanted to show. I just don't have it in me tonight. We're going to end this video, so thanks for joining me. And we just got the top end answer, the easy one. You know what I mean? You do the geometry to figure out what the hell that height is, and then go throw it into the master equation. There's the master equation right there. That was this video. I just wanted to be like, hell yeah. I mean, all the big colleges, that's what they teach, is just like, hey, you should be able to take a problem and just throw letters at it. You know what I mean? You lose all touch with reality, but it's kind of fun when it actually works. And then, I'm not going to save this, but it's just kind of cool. I consider it a magic trick. Because now you can change kind of any variables, but you can't. You know what I mean? So that's also what even though you have an equation that's based on variables, it's like, no, you can't. Because, to a certain degree, you do have restrictions in geometry. You know what I mean? All these letters can't be a negative number. So that's so... And then you might have restrictions on geometry. So even though you have an equation that looks like a master equation, happens all the time, where it's still, you can't use it for every situation. You'll even get equations where you can't even use it for like theta is equal to 0, because like, I don't know if you have weird, divided by whatevers, in the trigonometry world, stuff might just blow up. So anyway, alright, enough said on this, and hopefully this is just entertaining, but I guess I'll post it. I'm fine. It's good to make mistakes, but I'm having a hard time ending this. So thanks for joining me, and guess what? That's a video.